Hi guys, today I'm going to show you how to predict time series data using LSTMs in Keras. And yep, today we're going to use Python. So what is time series data? What are those things called LSTMs? And what is the task that we are going to do today? Let's start with the time series. So what is time series data? Time series data is probably some of the most common data that you're going to meet in practice. And the difference between time series data and like maybe images or text or so-called structured data is the fact that this type of data is most often not recorded at some regular intervals. So you can think of the data is recorded daily or yearly or monthly or whatever. And some of the examples for that type of data are maybe the fluctuations of the Bitcoin prices or the stock prices. You can think of the weather data as an example of time series data. And of course, there are more examples of that. And in practice, you can use time series data to predict something in the future based on the data of the past, if that makes sense. So the interesting thing about the time series data is that the assumption that your data is independent, like your data points are independent, is pretty much blatantly false in here. So we are going to have to build models that do not make that assumption, or that use the data as and predict the future data as the current value is based on the values that we've already seen in the past. So some of the most important properties of time series data are the stationarity or something like that, and the seasonality of it. The stationarity okay, the stationarity. A time series is said to be stationary if its mean and variance are pretty much constant throughout the time. So for example, I can show you some time series data like in this one. As you can see, the mean of this time series data is around 0, and yeah, there is a variation in the variance of the data, but it's pretty much the same. Like you can put some boundaries in here and in here, and most of the data, like 90% or more, will be in those boundaries over here. The other interesting property of those type of data are the trends, and you pretty much know what trend means. And as you can see in here, we have no trend at all. The last property that we are most probably interested in is the seasonality. The seasonality is what you might expect it is. It's basically some cycle or some amount of time in which the data is actually repeated or duplicated. And as you can see in this example right here, we can start from something like here, go like 5 steps into the future, and the data is pretty much at the same point. And then we can do the same thing again, and you can see that the data is roughly the same in each 5 step intervals. Okay, so this is time series data, and today we're going to use it to predict demand of bicycles. And those bicycles are something that are rented out in actually London. So the data is real, and we're going to have a look at it in a moment. The next thing that we are going to use today, or you have to learn about today, is recurrent neural nets. So recurrent neural nets are basically a modification of the regular or feed-forward neural nets that you've already probably know about, and they allow us to process sequence data. So you can think of sequence data as text, That is one of the most common applications of the recurrent neural nets. And the other sequence data that we have is actually the thing that we are taking a look at the moment. So that's the time series data. And you can use those recurrent neural nets to remember the past or the previous values of the data that you have. So that makes perfect sense for us, because we are going to predict the demand of bike shares into the future based on the history in our data. So how this neural network works? Basically, they have a thing called memory. So in this memory, you actually feed in the previous values of the time series or of the sequence data, and you have a regular units or neurons that compute the current value. So it's basically a simple layer in your neural network, but it also gets input from the previous layers or the previous values in the sequence of the data. One of the most commonly used in practice types of recurrent neural nets are gated recurrent unit neural networks, or GRUs, and LSTMs, which is an acronym for long short-term memory networks. So today we're going to have a look at LSTMs. Well, we are not going to discuss the theoretical implications of using LSTMs. The thing that I'm going to say though is that LSTMs are somewhat required in practice because of the gradient exploding and gradient vanishing problems that you might encounter when using recurrent neural nets. Those problems are particularly relevant because of the way that recurrent neural nets are trained, and they are trained using a modification of the backpropagation algorithm. The backpropagation algorithm is not able to train a recurrent neural net in its pure form, so a modification known as backpropagation through time is applied that actually unrolls, and you can think of flattening the recurrent neural net. So it basically creates a flattened or unrolled version of the recurrent layers in the recurrent neural net, and then applies a regular backpropagation algorithm. You can have a more detailed view on LSTMs and recurrent neural nets in the article that I'm going to link below. So let's start with the problem that we have today. So today, once again, we're going to use the London bike sharing dataset, which is provided by Hristo Mavrodiev. So this data is showing us historical data for bike sharing in London. So we're going to have a look at it and try to predict the demand of bike shares in the future. So as I've said in the start of the video, we're going to use Python and Keras. So the first thing that we are going to do is prepare or open a Google Collaboratory notebook. So I'm going to link the notebook again here in the description below. So let me just show you what I have for now. I have the installation of TensorFlow, the GPU version of it, and the gdown package, which we're going to use to download the data. And the first thing that you need to do is go to the runtime and change runtime type and check if you're using the GPU. So I'm using the GPU, and you should use Python 3. I hope so, at least. So the next thing that we're going to do is run this. This should install all those two packages and the necessary dependencies for these. I've already done that. The next thing that I have in here is a lot of imports and setting up of the random seeds for NumPy and TensorFlow. Unfortunately, when you use TensorFlow on a GPU, the seed doesn't actually work like on every platform. It's a really tough issue, and you can dive deeper in it, but anyway, I'm going to set it in here, but bear in mind that your results still might be different than mine. Okay, so I'll execute that cell too, and then I'm going to download the data from my personal Google Drive into this machine right here. So once this is here, let me just increase the font for you guys. Okay, so we have the data and it's around 1 megabyte, and if you go to Kaggle you should see that the data is right around 1 megabyte. So let me load the data into a pandas data frame for you. I'm going to read the CSV file in here, and I'm going to tell to London bike sharing CSV file. Then I'm going to parse the dates because we have a time series data, and I'm going to assign the index as the timestamp from the dataset. So the time step column in this CSV file is actually the time at which the data was recorded, and the data was recorded at regular 1 hour intervals or so, and we're going to have a look at the data in a minute. So I'm going to pass in the parse dates, and in here I'm going to specify the timestamp, and I'm going to say that the index column is going to be the same timestamp. Okay, so I'm going to run that, execute this, and see that we have the timestamp in here, parsed at date, and you can check that with df.index, and it should be datetime. Yeah, it is, and it is datetime index. So this makes the pandas data frame a bit more special, and I'm going to show you how you can easily plot some data in a bit. So the things that we have in here, or the columns, are T1, T2. These are, if we go to the data and go to the description, these are the real temperature in Celsius, and the temperature in Celsius in like how does the temperature actually feels like. We have the humidity in percentage, wind speed, kilometers per hour, weather code, which is a category of the weather. It means like, is it clear, clouds, broken clouds, cloudy, rain with thunderstorms, snowfall, and freezing fog. These are the categories that we have. We have, is this date a holiday? So if the date in this timestamp is a holiday, is it during the weekend, and what is the season? 0 for spring, 1 for summer, 2 for fall, and 3 for winter. Okay, so we have some categorical data, and we have some regular numbers or numerical scale. So that's all right. And the next thing that we are going to do is to extract some features from the timestamp. We're going to do a bit of feature engineering, and this is going to be mostly for the exploration of the dataset that we are having. So the first thing that I'm going to do is add a new column called hour, and as you might have guessed, this column is going to get the hour from the index or the timestamp, the hour of day that is, and you can easily do that with .hour. So we are going to do the same thing but for the day of the week, so Monday, Tuesday, whatever. Okay, and you can press tab to get the auto completion from the Google Collaboratory. This feels like it was significantly improved during maybe the last month or so. The next thing that I'm going to take is to the day of month, So this is going to be another integer. And the last thing that I'm going to take is the month itself. So 0 to 12, I believe. Okay, so this is the tiny bit of feature engineering that we are going to do. And if I go ahead and get the head of the date frame again, you can see that we have the hour in here, we have the day of week, day of month, and the month itself. So January is month with number 1, day of month, etc. You get the picture. Okay, so let's continue with some basic plotting. And the first thing that and sorry, I forgot to mention the count feature or column. This is the column that we're going to predict. And as you can see, the amount of bike shares for this interval, this 1 hour interval, at the beginning is 182, then it's 138, 134, etc., etc. So let's take a look at that data. And I'm going to use Seaborn line plot to plot the index, and I'm going to use the count, and I'm going to specify the data. So this is going to be a rather large plot. Let's wait for it. Yeah, here we go. So as you can see, we have a lot of data, and we have at times roughly, like, one of the outliers, I guess, is roughly 8k of shares for an hour, which is pretty amazing, I guess, if that's correct. But we regularly have right around 3 to 4k of bike shares per hour, that is, which is pretty amazing. So let's try to maybe get the last 200. Okay, whatever. I'm not going to try that right now. Okay, so the next thing that I want to show you is how to resample the data, because remember we have the data by hour, which is too frequent, I guess. We can do the same thing but resample the data by month. So we're going to take how many shares are there each month. So to do that, I'm going to use pandas resample, and I'm going to create a new data frame. So again, the resample method in pandas, and the rule I'm going to use is going to be the month, and then I'm going to sum the results. So we're going to take the sum for each month, and we're going to do pretty much the same thing. I'm going to copy and paste the data from here, but again I'm going to use df by month. So we should have a look at the new data, and here it is. Yeah, okay, that's better, I guess. You can see that the data is definitely having some seasonality component in it, so I hope that our model catches that later. And you can see that during the summer, I guess, the number of bike shares are significantly more per month, at least, than the other seasons. So you can compare the data, and you can see that this form of transformation of the data is going to give you some insight compared to the raw data that we had here. So this is pretty useful, I guess, at least when exploring time series data. Okay, so the next thing that I want to have a look at is whether or not the day of the hour matters when we have this kind of bike share or time series data. So to do that, I'm going to draw a simple point plot, and you're going to see what a point plot is. Again, from the Seaborn package. Again, we're going to use the raw df we're having, and for x I'm going to specify the hour, and for y I'm going to specify the count. So let's have a look. Okay, so as you might expect it, this shows us that during the 6 to 10 in the morning we have a lot of people that are taking or sharing, taking a bike. They might be going to work, or maybe going to school or university, whatever. There is significantly less, but more than the night hours demand for bikes during the afternoon, and then in the evening hours again we have another spike. So this is again pretty useful, because if our model knows the current hour of the day that we're going to predict for, we might expect that the number of bike shares should be maybe higher if the hour is 8 in the morning or something like that. So another thing that I want to show you is the number of shares when the day is a weekend or not, or holiday or not, whatever. I'm going to show you the weekend version of it, and I'm going to take the same code as we had over there, and I'm going to specify the hue, which is holiday. So remember, this is a Boolean variable in our dataset. So you can see that when the day is obviously a holiday with one or orange in here, we have a significant spike during the afternoon hours and not much else on the other side. So in the afternoon and then in the early evening we have much more bike shares compared to the regular or non-holiday days, where we preserve actually the observation that we had for the raw data. So again, this feature might be really important when building our model. Okay, so the next thing that I wanted to show you is another chart or a graph that is using the point plot method. So I'm going to take this and I'm going to show you the same thing, except that I wanted to graph on the x-axis the day of the week. So you might imagine that weekends or non-weekends are another important thing, and it really looks that way because Monday to Friday you can see a lot of bike shares compared to the weekends. So another important feature that we just added to the dataset using our rather simple feature engineering. So okay, the next thing that I'm going to show you is how to split the data, and we're going to split the data because we want to use some of it, or the first part of it. If I go back to the whole data, roughly speaking, we are going to split the data somewhere in here, and we're going to use all of this for training, and we're going to use this to check whether or not our model has really learned or is able to predict the demand of bike shares. So to do that, I'm going to use a train size variable, and we're going to take 90% of the data for training, and the remaining is going to be the test size, of course. And And then I'm going to split the actual data frame into a train and test variables. And then I'm going to print the shapes of the train and test data frames. Okay, so as you can see, we have around 15.5k examples for our training data, and we have roughly 2k examples for the test data. So, okay, the next thing that we are going to do is to transform the data, or to scale or pre-process our data, because as you might already know, learning using scaled data is sometimes faster and maybe more accurate depending on the data on your models, but LSTMs in general should at least benefit from scaling the data. So I'm going to use the robust scaler from sklearn, and I'm going to show you how to use it to transform some of the columns that we have in our dataset. So let's start with importing the actual scaler. Okay, the robust scaler we have here, and I'm going to create a variable that will list that specifies the columns that we're going to use for with our scaler. Is going to be T1, T2. Remember that are the temperatures, and the temperature feel likes in Celsius, so these are numbers. The humidity, the percent humidity or whatnot, and the wind speed in kilometers per hour. So I'm going to create actually two transformers, or two scalars. One of it is we're going to use for the for those columns, and the rest, the other one, we're going to use for the count data, and I'm going to show you why is that in just a bit. So I'm going to create the feature transformer, and don't mistake that for transformer models that we might have a look at in the future. And I'm going to create a count transformer too. So the way that this thing works is to call the method fit on the train data, and then we can transform that same data, but the fitting should be done only on the train data, because we want the test data to be something we've never we have no information about it during the training, so it should be simulated as some dataset that we don't know anything about. So don't make the mistake of scaling or fitting your scalars or pre-processing steps with the test data included. Of course, there are exceptions to that, but in general, you should never do that, actually. Okay, so the transformer, we're going to transform, actually to fit the train data, and we're going to fit only the columns in the features. And actually the latest versions of Panda do not recommend using the values method or property anymore. We have another method called toNumPy, which as the name suggests, returns or transforms the data frame data into a NumPy array. I'm going to do the same, literally the same thing for the count transformer. I hope I don't mess up anything. So yeah. Okay. So let me check if this works real quick. Okay, we don't have any errors. So I'm going to transform the train data with the feature counts, and then I'm going to transform the count and then I'm going to transform the test data. So let me just do that. The feature columns, and I'm going to call transform, and I'm going to transform on the same thing that we've did over here. So I'm going to transform the count in here. Okay. Okay, so we should have the training data transformed, and I'm going to do exactly the same thing on the test data. And this should work, I hope. Okay, we have a bunch of warnings for improperly indexing those columns, but I'm not worried about those at the moment. So this should work, and it should be okay, I guess. And the next thing that we want to do is to cut the time series data into smaller sequences. Remember that LSTMs actually use sequences for training, and to do that I'm going to introduce a simple, maybe not that simple at first, as you might have guessed, function called create dataset, in which we're going to do the cutting of the time series data into subsequences, you might say. So I'm going to call the function create dataset, and it's going to take in the X, or the features, the labels, Y's, and the amount of time steps that we want to use as a history for our sequence. And I'll put in a default value of 1. We're going to use something else in a bit. And in here I'm going to create two lists, X's and Y's. You'll see why in a minute. And then I'm going to run a for each loop for the subsequence that we're going to create. And this loop is going to iterate as the amount of time that we have data for minus the amount of time steps. So if you think about this for a bit, you should pretty much convince yourself that we are going to reduce the data by probably a lot, and I'll show you how much in a bit. But this is the correct number of iterations that we're going to take in here. Okay, so the values of the X we're going to take in by using the iWalk method, and I'm going to take all the values from the ith position to the ith position plus time steps, and I'm going to call toNumPy in here. Then I'm going to append those values, and the next thing I'm going to do is to take the Y at this time step position. So basically we're going to have a look at we're going to create this series that use the history for amount of time steps that we specify in the function as a parameter, and then we're going to predict literally the current value of the time series, or the current value of the Y's that we've passed in. Okay, so I'm going to take the Y value, I'm going to use again iWalk, and I'm going to take exactly this position, this value at this time step. So recall that this will actually not take the current value, this is non-inclusive indexing right here. So the last thing that I'm going to do in this function is to return the x's and y's, but I'm going to convert those lists into NumPy arrays, because we are working with NumPy almost exclusively, and pandas of course. Okay, so now that we have the function create dataset, we are going to specify the number of time steps we are going to take, and for the purpose of this demo I'm going to have a look at maybe 10 time steps into the history. So, well, that's a bit small if I think about it, maybe because we have like hourly timestamps, so we are only taking a look at we're only taking a look at 10 hours. So let me change that a bit. Let me do a complete day, 24 time steps. So we'll take another whole day in the history, and based on the day or the 24 hours before, we're going to predict the next hour, and let's see how we are going to our model is going to do using that data. So I'm going to create the X train and X test data along with Y train and Y test data. So we're going to create our actual training dataset and our actual test dataset in here. And I'm going to pass in as Y only the count, as we've already talked about. And then I'm going to pass in the amount of time steps, which is going to be time steps. I'm going to do the same thing for the testing data. And as a last step, I always, okay, let me just run that. And I always like to print out the shapes of the data, because you know. And of course I have a typo, so axis is not defined. Okay, so yeah. Okay, so I guess this should help. Sorry for that one. Okay, so it might take a while for your data to be completely processed, but at the end you should receive something like that, where you have the number of training examples, 15.5k. We have 24 time steps into the history of the data, and we have 13 because we have 13 features in our dataset. And we are going to predict exactly the number of training examples in here. So these two numbers should be the same. So if I put a comment in here, I'm going to say that the shape of this thing, the X train, is going to be the number of samples, the number of time steps, and then the number of features. So you can think of create dataset as converting your data into this, or reshaping into this format. Again, I would like to see the same thing for the test data. And in here, we should expect just a smaller number of samples, but the other shapes should be the same, and of course they are. Okay, I hope that this makes sense. You can probably have a look at a simple sequence in here. If I go X test and get the first sequence, I should expect that this has 2413, of course, as a shape. And I'm going to take the first row in here, and I expect to have 13 values, which are going to be actually the number of features that we have. So if I go and get the shape for this, it should be 13. Okay, so if I do the same thing for the train, again, it should be 13. Okay, so we have our sequences ready to go, and the next thing that we are going to do is actually build our LSTM model. Fortunately, Keras does this pretty well, and I'm going to show you how to build a really simple bidirectional LSTM model. The bidirectional LSTM model is an LSTM model that not only looks into the history of the data, but also it looks into the future of the data, if that makes sense. So our model is going to be able to to learn from both the past and the future in the data, or the history and the future of the bike demand predictions on the bike share counts. Okay, so let me start by showing you how to create the model, and I'm going to build a sequential model into Keras, and I'm going to add in the first layer, which is going to be the bidirectional layer. That's really simple. And in the bidirectional layer, I'm going to put in the actual LSTM layer. Okay. And in here, I'm going to specify the parameter known as units, or the number of neurons that this layer is going to have. And the next important thing that we are doing here is to specify the input shape, since this is the first layer of our neural network. Okay, so what are going to be the shapes of our data? A really important thing that we have already done is to print the shapes of the training data, and Keras actually takes care of this value for us, so we only have to input the shape of those two. So to do that, I am going to take the shape of the X-trained values and put in the first index. So the first index is 24, and the second index, which is going to be the third value in the shape array, which is going to be 13. So this should pretty much do the work for us. The next thing that I'm going to do is add a dropout layer, and the dropout layer is going to regularize, or maybe penalize more complex models. You can try out different values of the dropout, and you can try a model without using a dropout, but I guess that in our case we had a well, the dropout can help a little bit. So let me add that. And I'm going to put in 20% or 0.2 rate for the dropout. And the last thing is going to be the the output layer, and the task that we have at hand is regression. So we're just predicting a single numerical value. So to do that, I'm going to put a dense output layer with a single unit or a single neuron. Okay, let me do that. And I'm going to use the dense or fully connected layer, and I'm going to specify the amount of neurons, which, as we've already discussed, is going to be 1. Okay, so this is how you build a model in Keras. Nothing scary or something like that. And this is actually quite a complex model. It's a bidirectional LSTM. The Keras API is really nice. Okay, so the next thing that we are going to do is to compile this model. This is required, and we are going to specify the WASP function against we are going to compare our results, and we are going to use an optimizer known as Adam, which is going to be, we are going to use that one with its default values, and it should do fine in our case, I guess. So let me specify the mean squared error, and I hope that you know what this mean squared error WASP function is. I'm not going to explain that in here. and the Adam optimizer. So, okay, let's compile that. It should work. Okay, so now that we have our model, it is defined and compiled, we are actually going to train using the fit method on the model. And the training process is going to take a bit, but let me show you how it should work. The training model is, the training process is, the method fit is returning a variable known as history, an object known as history, and we're going to use that to plot the training process later. But let me start with fitting the model. The first two parameters are going to be the data, X-train and Y-train. We're going to train for 30 epochs, and the batch size is going to be 32. So the number of epochs, I hope you know what this means. It means that the data in the training data is going to be seen 30 times, or will be used 30 times by our model. And the batch size is the number of sub-samples that our model is going to take when training from a single step, if you will. Okay, so the next thing I'm going to say is that we're going to use some of the training data for the validation of our model. Remember that we don't want to use our training data. Our training data we're going to use only at the end to have a look at how well our model is doing on future data. So we're going to say validation split 0.1, so we are reserving 10% of the data. So that's like 2k examples for validation. And we don't want to actually shuffle the data when training, because again we have time series data, and time series data is dependent on the time that is stored. So I guess it should make sense that we don't want to shuffle the data. Okay, so this is pretty much the way it should work. Let me start that and see if everything is working as expected. And hopefully the training process should start. Okay, so something is already starting, and you can see that the model is training actually pretty fast, I guess. And I'm going to pause this and continue once all of this is trained. Okay, so the training is already complete. It actually did it quite fast, I guess, but we're using a GPU on Google Colab, so the model is also not that complicated. So let's have a look at the final validation was. We have 0.0231, which I guess is quite good. Let me plot the loss for you, and we're going to use the history. And we're going to label that as a training loss, and I'm going to specify the validation was in here, and I'm going to show the legend to know which one is which in here. Okay, so as you can see, we have actually pretty well trained model, I guess, and we only need something like maybe 10 or 15 epochs to create a really good model. And you might say that maybe a bit more training might help with this model and get even more accurate validation was, but I'm not so sure. You can try it out, I guess. Okay, so let's actually see some predictions from our model, because only looking at the loss doesn't tell us a lot, I guess. So the single thing that I'm going to do right now is get the prediction from our model. And I'm going to predict on the test data, of course. Remember that our model haven't seen any of it right now. And the thing, one of the most important things that we're going to do is to invert the counts, because we want to see the actual amount of counts or the number of bike shares that we want to display in the plots that we are having. So remember that we've used a robust scalar, and we're going to inverse that scalar. And the important thing in here is that we have a robust scalar exactly and only for the number of bike shares. So this is why we needed this. There might be better ways to do that, but I've just created a transformer or scalar just for the counts. So let's inverse the transformations. I'm going to get the inversed values of the training data, of the test data, and then of the predicted data. We have the inverse transform method, and I'm going to reshape the training data because it won't work otherwise, because the shapes are pretty messed up, I guess. And I'm going to invert the white test data, and finally I'm going to invert the predicted data. And in here we actually don't need the reshaping. So we have the actual counts or the number of bike shares. The next thing that I want to do for you, and you might want to do as well, is to actually see the number of the amount of predictions that we have and how well those predictions are made for the bike share counts. So first I'm going to plot the test data, and I'm going to take the inverted values, flatten that, and I'm going to mark that with dots, and I'm going to say that this is the true values. Let's just start with this chart for now. And as you can see, these are the predictions. We have roughly, you can see how many examples we have in here. So recall that these are the true values, the true number of bike shares. And the next thing that we are going to do in here is to show the predictions, of course. And I'm going to specify the color red, and the label is going to be the prediction or predicted. And I have not defined this. Oh, my mistake. I have a typo in here. Okay, so let's wait for that. And these are our predictions, which are pretty good, I guess. I can apply the same marker to those, I guess. Let's see. Okay. So recall that our model is able to predict only the next value from the data, and as you can see, the model is doing quite well actually. It doesn't quite capture the most extreme values over here, but if you have a look at the values that are below the maybe 3K or something, or maybe 2.5K, you can see that the model is matching those values quite well, or it's quite close. So those extreme values are quite hard on our model, but in general it seems like the predictions are pretty good, I guess, for such a simple model. Of course, you can try a lot more techniques to improve the model, maybe add even more data, or why not one-hot encode some of the categorical values, because we haven't done any of that. And this is pretty much it. I hope that you like this. Please like, subscribe, hit the bell button, whatever. And I'm going to link this notebook in the description below. I'm going to link in the two tutorials or guides on time series data. And let me know if you want to have a look at a video that shows how to use time series data for classification, in particular classifying or human activity recognition from time series data, and how to look and find anomalies in time series data using autoencoders. I think that this is pretty cool applications of LSTMs to create autoencoders and detect anomalies or outlier detection in time series data. Thanks for watching, guys. Bye. I'll see you.